Well, we've come to this place. We're finally doing some complicated stuff. Now we're going to try to estimate a population mean using the sample mean. So it's a little bit of a convoluted path that we take. We go like this. Say if we were sampling from a normal population, X bar has a normal distribution, and X bar, sorry, if we're sampling from a normal population with mean mu and standard deviation missing, sigma, like that, then X bar is normally distributed. It has mean mu and standard deviation sigma over root n. And if I compute X bar minus mu over sigma over root n, I get a standard normal distribution. We've done that. Okay. And then, of course, the problem with what we're trying to do here is we don't know much. So we're trying to figure out what mu is. We probably don't know what sigma is. We only have X bar to work with. We know if we did X bar minus mu over sigma over root n, I'd get a standard normal. So I know the kinds of numbers that come out. So I can do probability calculations, except sigma is not known. So if sigma is not known, we estimate it with S. So we put S, that's the sample standard deviation. So we sample, we put the sample standard deviation into the Z formula. If we place this in the Z formula, we no longer have the standard normal distribution because that's random and normal, but that's random and something else. And you're taking a ratio there. So the exact shape of that distribution is subject to debate. In any case, the thing you do get is called the T distribution. And it was used before anyone actually could create tables of T values because that was the only way you could do things. And they thought, well, it's pretty close to Z. So we know it's not Z, so we have to be a little conservative in how we use it. But it's pretty close to Z, so we'll try to work around it. And then a fellow who was working at the Guinness Brewery as a quality control guy who did math on the side in addition to doing quality control for a living, discovered the formula for the density curve for T. And once we have a formula for the density curve, then we can mechanically make the tables that we need, either through numerical integration or other techniques. So you're not guessing, you can actually get actual values, and that information that showed what the T distribution looked like was published by this guy who worked for Guinness Brewery, but he wasn't allowed to use his name. And so he published it under the name of Student, figuring people would know a student was a real name, but now it's called Student's T distribution. And his name is not lost, but it's lost generally in the textbooks. So he kept it a secret. So that's Student's T sitting right there. And so the shape of that, since that's random, it still has a bell shape. It looks a lot like Z. So it was usable anyway, but now they had a formula for it that could do more accurate versions of confidence intervals and what we call hypothesis testing. So this thing here, though, this T, is a different shape for each sample size. We said we were lucky with the normal distribution when we did X bar and standardize it by computing a Z-score, that you get the same distribution every time. Here we're standardizing it by computing like a sample Z-score. And when you do that, you get a different distribution for each sample size. And so the tables have to list the values for each sample size. They're slightly different. Even so, Z and T are pretty much the same value. Even across the different sample sizes, T matches to some extent the Z you'd expect to see in that situation where N wasn't referenced. Okay, so to complicate matters, it's common to list critical values and probabilities according to degrees of freedom, which is N-1. So we're going to use critical values for T, but we have to use critical values based on the degrees of freedom. That's just historically the way people look at T tables. And then we want to see that we can't get a hold of the confidence interval formula as easily as we did for proportions, but we can try this. We can say this quantity here has a good chance of being between these two numbers. And so we can change that set of inequalities into an inequality that has mu on the inside, which say mu would have a good chance of being between these two numbers. Like that's algebra right there. We don't really care, but it is. And then rewriting that, it's apparent the confidence interval for mu is x minus t alpha over 2 s over root n and x bar plus t alpha over 2 s over root n. So it looks like this. So with a little bit of work, we can get a confidence interval formula, and then it makes sort of more sense now that it looks like that, because it looks like an estimate plus or minus a critical value times an estimated standard deviation. So that's pretty well the usual way confidence intervals look. Estimate, critical value, estimated standard deviation. So it's there. It's not hard to remember what it looks like. So with our proportion, it was p hat plus or minus z alpha over 2. And then here we had the estimated standard deviation, square root of p hat 1 minus p hat over n. So now we've got the value, estimated value, a critical value, and an estimated standard deviation. So it follows the same plan. So let's look at the tables so we figure out how to do that. So here we go. So here's what the t tables look like. So on the left side here, I've got degrees of freedom, which is n minus 1, like that. And then across the top, I've got the tail probabilities. And on this side, then it's degrees of freedom. In the middle here, I've got the critical t values. So that would say, if n was 25, say, maybe I'll put this where I can see it. If n was 25, you want 95% confidence interval using t. The t alpha over 2, 0.025, we have to find it. That's going to be in there because it's going to be x bar plus or minus t alpha over 2 sigma, s over root n. It looks like that. I wrote sigma, but I was just thinking standard deviation. So I need t alpha over 2 for 95%. Alpha is 5%, alpha 2 is 2.5%. So I'm looking for the tail probability to be 0.025. So I come into this world here, and I found the right tail here. It's 0.025. Okay, so we're looking at this column of numbers. And then n is 25. So degrees of freedom, it's n minus 1, that's 24. So I go down to 24 here, come across. And there we have the critical value is 2.064. So there you go. Now some bad stuff happens down here. So I've got all possible degrees of freedom here. And pretty soon it starts jumping around. So we'll get close to the bottom. I go to 40, it's all good. Then things start happening, 40, 50, 60, and so on. So we'll make a note to ourselves that if your degrees of freedom is not listed, use the next smaller degrees of freedom instead. So if your sample size was 45, say, so if n was 45, degrees of freedom would be 44. I'm looking here, I don't see 44. I'm going to have to use 40. Use degrees of freedom equal to 40. Now, you don't do a lot of damage because between 40 and 50, not a whole lot is happening. Here we are out in our 5%. Well, things are happening a little bit. 2.021, 2.009. Stuff is happening, but it's not a very big change considering you're going 10 steps. If you look back at the other ones and you go 10 steps, say from 30 to 40, maybe you see a slightly bigger difference than from 40 to 50. So they just stopped giving you have to fit it on the page. I would have stopped earlier and put them closer together. But everybody that makes a table has a different way of doing it. I've got another one here. Where is it? Oh, this one. So this one here, which we'd have to zoom in on. Here's another one, a T table. Let me zoom in and see what it looks like. So that goes 30, 35, 40, 45, 50. So it splits the difference a little bit differently. So every table is a little bit different. This is one out of our book right here. And then you'll notice at the bottom here, let me zoom in there. The last row sometimes is called infinity because these are getting bigger and bigger. And so, but then sometimes they call it Z. So this last row, you know, when the sample size gets large, T becomes Z. So the areas will become Z areas as the sample size grows large enough. So more than 1,000 pretty much. These numbers are recognized as Z values, 1.96, 1.645, 2.82. I know those numbers by heart. Those are Z numbers. And so if you need the places, the critical values for Z, and you don't have a table of them with you, but you do happen to have a T table with you, just go to the bottom of it. And if you wanted to know, say, 95% confidence interval, so the T alpha over 2, the alpha over 2 is 0.25. The bottom here tells you what the Z value is. And then if you're using a T instead of a Z, you head up to the degrees of freedom and the number changes a little bit. But look at this, at 24, it's 2.064, and Z is 1.96. They're pretty much the same number. So that's supposed to help you use the tables, and then I can assume you can do it. And I'm going to go back into my learning classroom and continue this story and finish. This is section 9.2 we're doing. And there we go. I can stop this.